Syd Visser. Oops.
Sorry.
That's all right. Sorry about that.
Don't get any slides either.
I
so-
know.
Well, I was going to use my own machine, but the HDMI didn't work here.
There we go.
And if I'd done that, I would have used my cell phone to run the slideshow. It's this new app I got that runs LibreOffice, and I could use it as a pointer and everything. Now I'll have to go to old technology and use this pointer and stuff. So this is about the talk on the Ootsa property. It's not 4310 compliant. And I'd like to acknowledge Shane Ebert, who's VP of Exploration, and Conrad Swanson, who I think now is not the chairman anymore, but he was when we did most of the work. And then everybody else who was involved in it. There was so many people involved in this project that there's a long list. So I'll quickly go over geology and the location, and then the big thing is the history of the project. We worked on this for about 10 years, doing increasingly more work on it. And then in 2013, we actually did a comparison survey with some of the earlier data, which will be kind of my main focus. And then, if I get time, I'll go into looking at decimation of some data, some stuff that Brian Chen has been working on for us in the office here, and it's really preliminary stuff. So I'll see if I have time for that. It's 100% owned by Goldreach. It's a polymetallic porphyry type system. The seal and ox are copper, gold, and molybdenum. Mainly copper, a little bit of gold, and there's some silver in it too. It's very close to the Huckleberry mine. It's part of the west coast of America's porphyry systems, and it's located in about central BC on the west coast. More exact, it's located right on the western edge of the Stikine terrain, just before you get into the Coast Mountain. So it's about 4 west as you can go into the Stikine. A little closer up shot, it's to get in there, you go from Prince George up to Houston, and then you take the mine road to Huckleberry or Logan Road to Mine Roads, and then you it's right in here across the Huckle Reach. Just a little bit about geology. It's mainly Jurassic volcanics and sediments intruded by Cretaceous intrusives. And some of the early work was done in the 1900s. They discovered a vein-type deposits of gold, lead, and zinc up in Yenamo. And then the Huckleberry mine was founded in 1960 and went into production in 1998. And it's been off and on in production since. I think it's closed down again. And then the seal, which was called the lean-to, was discovered in 1968. This is the property map, the claim map from Goldreach now. I think this is kind of up to date. There's a Huckleberry mine, and there's the ox and the seal in here. There's a lot of other showings on the property too I won't go into. To get there, you have to go across from Talca Reach on a barge, or by boat, or by plane, or somehow. There's no road going there, and this is you can see the White Seal Range mountains in the background. The seal is, where'd that come from? Microsoft.
It knows it's you.
The Goldreach is in kind of the flats here before you get into the range, and this is looking back at Talca Reach. You can see when we started there by the age of the truck. I think that's John Eschner's, and he was still working for us. So we've been up there for a while. Once you get on the property, you can see back at Talca Reach, and there's a Huckleberry mine across the water there. So geophysics, let's go through the historic stuff a bit. This is a closer look at the geology of the property. Again, you have these sediments and some volcanics, and they're intruded by these younger intrusions here for the ox deposit, and here's the ones on the seal. And there's probably some hidden ones around here that aren't showing up in geology. A lot of work was done from 68 to 89, the typical kind of work, geochem, prospecting, trenching, some drilling, a little bit of IP, some MagVLF and stuff. And from 1990 to 2003, if anybody remembers, was kind of a dead time in BC, so really nothing was done. And in 2003, Hans Smith from Grady Resources asked us to look at some historic IP data, and we inverted it. It was collected by Edgar, Beretta, and Ellis, if everybody remembers them. And we inverted it, and this is the inversion we got, which showed some interesting chargeabilities, and it also showed this interesting resistivity anomaly here that was sitting in this chargeability low. So in 2004, he hired us to go up and redo that survey with what was then kind of modern methods. We did a couple of 2D lines, and we did some IP survey there, some modified offset pole dipole 3 lines at a time. That was our early start to getting into 3D work. We were still using fairly old equipment then, like the Elric receivers and stuff like that. And this was the results from it. Again, you can see this resistivity high here, and these chargeability anomalies. So looking at the 3D actually showed that the outline of the chargeability a lot better than the 2D did. And this was kind of interesting, so they wanted to extend that. We also did mag, and this is the mag response from the seal property. It seems to be a younger kind of barren intrusion that probably remobilized some of the minerals around there. This is just another way of looking at it. That was our early presentations. And this is the drilling on the seal property. You can see the copper results in the drill holes there. In 2005, we went back to extend it, and we did some 3D IP work, and we still did some 2D lines because at that time it was still tethered arrays, and you had to have everything wired together. So there were some cliffs in here in a gully, and it was easier to actually do 2D over them at a time. Now it's easier to do, with our new equipment, it's easier to do 3D over in areas like that. And this is the results. You can see the outline of the chargeability anomaly there. And this was the mag results. The mag seems to go in kind of the opposite direction, or 90 degrees to the chargeability trend. I'm still not sure why. And this here is kind of in the Damascus area, which is kind of interesting. 2006, we extended again a little bit up in here, just for the Damascus vein. There's a vein deposit there that was discovered by Kaminko. And this is the results from that survey, and as you can see, the chargeability, there's really nothing that shows the Damascus vein. This is the seal and the west seal. The west seal was discovered actually more by drilling after, and this anomaly has really never been tested. But if we look at the resistivity, it's really interesting. I had animation here, but it doesn't work because I got a PDF file. So this Damascus vein really lies along this structure here, this sharp break between resistivity. And it's a vein deposit, so that makes sense. It comes up along structures in that contact zone. And the seal deposit here, again, you see you have that high resistivity sitting in the middle of the seal deposit, which is probably from an intrusion. And this is just looking at it from the south to the east. And the white seal range here, the west seal, the seal, and this is the Damascus. In 2007, we extended, they acquired the Ox property, which was owned at that time by a separate company. They acquired it, so we did a survey over the Ox deposit. The Ox is really different, and it's very interesting. You can see this really clear resistivity low around this resistivity high, and you see this horseshoe kind of shaped chargeability anomaly. It's too bad we couldn't go down here at that time because this is a really steep cliff, so it was never really extended down there. This is showing it again, and it shows the drill holes. You can see that it's all drilled along, so they drilled directly on the chargeability anomaly, and that's where the mineralization is. And you can also see there's a magnetic core to this. So in 2009, they did a large airborne magnetic survey there, which I won't go into. Trent probably knows a lot more about that than I do. The only thing I'll show is that the seal itself, it's got this magnetic anomaly there, and the mineralization is kind of around it. And there's the west seal, which doesn't seem to have a magnetic anomaly, which was kind of surprising because it seems to have a fair bit of magnetite with it. And there's the resource model you can see over there's the seal and the seal west. So most of the resource here is a little bit deeper. In 2011, we extended it again. We went into this area to follow up mainly the magnetic trend, kind of went that way, so we expanded on it. And in 2012, we extended things again a little bit. And then in 2013 was kind of our last big survey up there. And we went into this is when we designed our 5-line diamond array, 3D array, and we had completely new receivers. So this was quite a different survey. So quite a bit of different equipment was used on these surveys, about 4 different generations of equipment. So, and we also did a kind of a comparison survey. We kind of did this on our own at the end of the survey to go over the seal deposit again, to compare the old 2D, 3D kind of data that was collected in 2005, 2006. I'll talk about that a little bit more later. In 2014, we compiled all the data together, which was quite difficult because of all these different instruments that we used during the survey, and especially because the client wouldn't really give us enough money to do good overlaps in some of these areas. So it was really difficult to put together, but I was surprised at the actual results we got. So we can actually see the anomalies here. Here's the seal, here's the ox deposit, and there's some new ones there. So from that, you can see these two distinct trends. You can see this one trend up here in the north that goes like to the Huckleberry mine, and then there's what they call the seal trend. Again, the mag seems to be going more in this direction, not sure why. And this is some of the exploration targets that are still open, that they're still hoping to raise money for to work on. So there's a lot more targets in the area, and especially on the seal itself. There's this whole area here to the southwest that really hasn't been looked at. These are chargeability anomalies. So the deposits here actually seem to be in the kind of quote chargeability lows. This is so I'll go into this comparison survey we did. Here's the 3D part. So originally the surveys was done there with 2D expanded array and very modified 3D, and it wasn't designed to look very deep because they thought at that time anything deeper than 200 or 300 meters wasn't worth looking at anyway, because everybody was talking about open pits. So nobody really cared if you see deeper than that. Nowadays, when especially the seal west here, which is probably, most of it is deeper than 300 meters. So we wanted to see if we could see that. So we improved our survey design, improved our equipment, and very significantly improved depth penetration. I'll show. This is the survey design. So we did 200-meter line spacing. 2-kilometer long lines, which probably should have been a little bit longer for the depth we see. And the instrument we used our new Volterra digital acquisition unit, which is a complete distributed array system, and each unit has 4 channels, 24-bit, full waveform, and we use a normal GDD transmitter. We acquired 5 lines at a time. So we had 2 receiver lines here with these diamond kind of arrays, and we had 3 current lines operating at once. So the dipole was 400 meters by 50 meter diamonds, and the dipole length was about 210 meters. So we had 72 active dipoles. So those people who still think in terms of n, it's n equals 1 to 72. And when we moved over to the next five lines, we overlapped one current line in the middle here. So that's why you see these extra readings here. The remotes, we always put the remotes fairly close to the survey site so that we could use them, incorporate the remotes in the inversion. So here's one remote, there's one remote. And for this particular job, we also put two remotes off to the side, which we collected some currents from. We didn't do every current from those, but from these we did most of them. So here's some results from that survey. You can see this outlines the seal west, and this is the outline of the of the seal east. You can see here, this is resistivity, chargeability, 100 meters below topography. These are inverted results. And I'll just go through these quickly. And here's a 3D view of the resistivity. As you can see, there's that resistivity height that sits in kind of in the middle of the seal west. And the chargeability is really kind of complex. You know, as you can see, we certainly didn't notice that on the previous surveys, but it's like really complex. You have these really high chargeability pods kind of around it. And as you can see, it surrounds the deposit. This is the deposit model. And you can see the high chargeability kind of surrounds the deposit. So it's almost like it's sitting in a chargeability low. A better way to look at it is probably compare it to a section that I took from Gold Reach website. And we look at the section, you can see the outline of the, I believe it's 0.2% copper is this blue line, and 0.4% copper is this red line. These are sediments, and this is the younger intrusion. There's some minor volcanics and stuff in there. Stuff too. Now we compare that to our chargeability anomaly. This is our chargeability. We can see the high sitting around here. If we compare it directly, I don't know if you can see it. You can see the high chargeabilities in here. That's the high chargeability anomaly. And this is the main zone here. But as you can see, there's still a weak chargeability in here compared to this. So it's still chargeable. It's just that the surrounding rocks, it's mainly barren pyrites, are really, really chargeable. And this is the resistivity, and as I mentioned before, you see that high resistivity kind of going through the deposit. So it's probably part of this younger intrusion. So how do they compare? This is a comparison of the resistivity. So this is the 2006, 2005 data from the 2D and 3D. And this is a new, you can see this one is much more complex than this one. We were actually surprised at how much near surface detail we got out of it compared to the other surveys. This is going down 200 meters. And you can already see that the earlier surveys are getting washed out. So you barely got 200 meters or more. This is still, you know, it still shows that these complex structures. And this is going down 400 meters, and the earlier data is completely washed out. I mean, that's there, and you're still seeing very good data. You still see this resistivity high and those resistivity lows in this data. So compared on section, these black lines here, these contour lines is the 2006 data from the 2D, and the rest of the section is from our new survey. You can see we're easily getting down to around 500-600 meters. We're still seeing good data. And this is the chargeability, shows similar things. It's very much more active. It still outlines the main zone very clearly, but and there's 200 meter depth, and you can see it's already starting to get washed out on the 206 data, and there's still a lot of detail in the 2013. And at 400 meters, it's kind of completely washed out, and there's still information in this. So if you compare that again, the black lines are the 2006 contours, and the color down here is the 213, and here's you can see the outline of the deposit of the ore in here. So you can see that it's in that kind of weakly chargeable zone in here. So it isn't, it's not with this really low chargeability. So just talking a little bit more about the array here is we used about 144 dipoles and approximately 200 currents. So we collected about 14,000, 15,000 individual readings. I don't think those numbers are quite right. I just picked them out, but that's approximately what we did. So this is, Brian did this. This is just looking at what it would look like in density-wise when you plot all these vectors and stuff like that. So the question was, are we collecting way too much data and overdoing this? So we did some tests. And, so we did some tests and we inverted using the remotes only. And then we inverted again by placing just 4 currents on each line. So deleting all the other currents. So we still use the remotes and 4 currents in the middle. And then we inverted it also by, we had interlacing diamonds, and we inverted it by taking one of the set of diamonds out. So this is the results from just using the remotes, which is actually very similar. It's basically a gradient survey. And as you can see, we outlined the chargeability anomaly quite good, but there's really not much detail in it, and the depth information also isn't very good. Now it could be that we got to put some more weighting functions on the inversion. This is very preliminary stuff. Brian started working on it, and then we got busy and we ran out of time, so we didn't do as much work on it as we hoped. This is just putting 4 currents along the line. Right away you see much more detail in the data, and it's actually not that far from our final results from having all the currents. And then we go with just a single receiver diamonds, and that's basically exactly the same as having the double diamonds in there. So, so you really have to do as many currents and receivers as we do. Personally, I like this idea of going to less currents and taking longer readings, because I think in most cases IP surveys don't take long enough readings. They take 10 cycles and run to the next station because they got to get production done. And really, when you do processing, 10 cycles is not enough to stack properly or to put proper filters on your data. You need at least 30, 40 or more cycles. So most of the time when we do IP, we're in such a production rush and everybody wants so many currents. I think we're way overdoing it. So that's kind of, the questions I got on here. And this is kind of my conclusion for that. I really think we overdo it with currents. It's a good idea to do a lot of receivers. I mean, the one advantage of it is that if you've got any bad data at all, you can throw it out, because you can throw probably half of your data away and get the same results, as long as it's not clustered in one area.
Thank you.
Thanks.
All right, we probably have time for one question, and then we can grab Syd at lunch if you have any more.
What was the sampling rate of your measurement?
I think you mean samples per second?
Yes.
Depends. Sometimes we do 1,000 samples per second. I think in this case we did 4,000, because I didn't show it, but we also on this test survey collected some MT data. Okay. So we wanted to go a little higher.
Nice.
So I think this was collected at 4,000 samples per second. So if I do EM type work, then I collected 32,000. So we can set the sampling rates of our data loggers to go anywhere from 128 kilosamples per second down to 1,000.
Yeah, and then you showed that image that where you have a big pyrite and then the mineralized zone having like moderate chargeability. Have you looked at like kind of spectral, because like you're integrating a certain time window and inverting that just chargeability. Have you seen like sort of spectral, like different time windows and kind of inverting that? Or
no, we haven't really seen any of that. I mean, we did some work on spectral data, and both us and Kingman kind of came to the conclusion that you got to go out to about 23 seconds if you really want to see spectral data. So when you do 2 seconds on, 2 seconds off, you're really not in the, right? And there isn't hardly any EM coupling in this area either, because I mean, we're looking at, 400 or 500 ohm meter or higher background, right? So we've got very little EM coupling, so there's, yeah, so no.
All right, well, thank you so much, Syd. If you have any more questions, we can grab them at lunch.